All right, let's talk about the single biggest, most important rule in all of statistics. Seriously, once you get this, it's going to change how you look at pretty much everything. The news, weird health claims, you name it. We're talking about the huge difference between two things just happening at the same time and one thing actually causing the other. It's a classic puzzle, and today, we're going to solve it.
Okay, so here's our game plan. We're going to start with the puzzle itself. Then we'll learn how to name our suspects, which, in stats, we call variables. After that, we'll go hunting for the hidden clues that can throw us off the scent. Then we'll look at all the different ways statisticians can gather evidence. And finally, we'll land on the absolute gold standard for proving that one thing really does cause another.
So, let's kick things off with part 1, the causation puzzle. We're setting the stage here with a super famous example. It seems pretty simple at first, but trust me, it's full of statistical traps.
Get a load of this. If you look at the data, you'll see a really weird pattern. As ice cream sales go up, the number of shark attacks also goes up. They move together, almost perfectly. So I mean, the data is clear, right? Does that mean we should ban ice cream to protect beachgoers? Of course not. So what in the world is actually going on here?
And this brings us to it, the golden rule, the absolute bedrock of good statistics. Just because two things are correlated, meaning they follow a similar pattern, it does not mean one is causing the other. You gotta burn this phrase into your brain. It's the key to cracking our whole delicious, dangerous mystery.
So, when a statistician wants to figure something out, they've basically got two tools in their toolbox. On one hand, there's the observational study. Here, we're just like a nature photographer hiding in the bushes. We just watch, we record, and we look for patterns or associations. But on the other hand, there's a designed experiment. This is where we put on the lab coat. We don't just watch. We actively interfere. We change something on purpose to see what happens. And here's the kicker. Only that second method, interfering, can actually prove causation.
Okay, on to part 2, naming the variables. You know, to solve any mystery, you first have to identify your suspects. In statistics, we need to get our language straight and figure out what we think is the cause and what we're measuring as the effect.
So first up, we have the explanatory variable. This is our main suspect. It's the thing we think might be causing the change, the one that could potentially explain what we're seeing. In our shark mystery, our first incorrect guess might be that ice cream sales is the explanatory variable. And then, on the flip side, you have the response variable. This is the outcome, the effect we're actually measuring. So, in our case, that would be the number of shark attacks. The entire game of statistics really is to figure out if the explanatory variable is truly affecting the response variable.
All right, now this is where it gets really clever. The most crucial part of statistical detective work is realizing that sometimes the real cause isn't either of the two things you're looking at. The real culprit is hiding just off stage.
And here it is. We call this the lurking variable. It's the secret third wheel, a hidden factor that's pulling the strings behind the scenes. It affects both of your other variables independently, which creates this illusion, this mirage, of a direct relationship between them.
So let's solve our mystery once and for all. The lurking variable here is the summer heat. Think about it. When the temperature goes up, what happens? Well, two things. 1, more people buy ice cream, and 2, more people go swimming in the ocean. And when there are more people in the water, that unfortunately just increases the chances of a shark encounter. The heat causes both things. The ice cream and the sharks, they have absolutely nothing to do with each other.
Now this is a super helpful way to keep two tricky ideas straight. A lurking variable is like a ghost. It's a factor that wasn't even included in your study, like the temperature wasn't in our initial data. It's haunting your results without you even knowing it. Confounding, on the other hand, is more of a mix-up between two variables you did measure. Like if you use a new fertilizer and you start watering your plant more, you can't tell which one made it grow. Their effects are all mixed up. The big difference is whether that hidden factor was part of your study or not.
So now that we know all about these hidden traps, let's talk about the different ways statisticians can run those observational studies we mentioned, the methods they use to just watch the world and gather clues.
First on the list is something called a cross-sectional study. It's pretty much what it sounds like. You're taking a slice of the population at one single moment in time.
Yeah, the focus here is 100% on the present. It's like taking a single snapshot photo of a crowd. It's fast, it's usually cheaper than other methods, but it can't tell you a thing about how things change or develop over time. It's just one moment, frozen.
Okay, next up is the case control study. Now, with this one, we're not taking a photo of the present. We're more like detectives reviewing old case files. We're looking backward.
Exactly. This is a retrospective study, meaning it looks into the past. Researchers find a group of people who have a certain condition, those are the cases, and compare them to a similar group who don't, the controls. Then they dig into their past to see what was different. It's awesome for studying really rare diseases, but its biggest weakness is that it's totally dependent on people having accurate memories or good records.
And that brings us to the third and probably the most powerful type of observational study. It's called a cohort study.
This one is perspective, which means it looks to the future. You gather a group of people, your cohort, and then you just follow them for years, sometimes even decades, tracking data to see what happens to them over time. This can give you incredibly powerful evidence, but as you can probably guess, it is super expensive and takes a very, very long time.
Okay, so if observational studies, even the really good ones, can still be tripped up by lurking variables, what's the ultimate answer? How do we get that rock-solid, undeniable proof of cause and effect?
Well, you might think, hey, to get rid of all the uncertainty, why don't we just collect data from literally everyone? And that's a great idea. It's called a census. You get information from every single individual in the population you care about.
And if you could do a census, your data would be perfect, 100% accurate. You wouldn't need to do any fancy statistical work because you'd have the complete truth. But here's the massive trade-off. It is unbelievably expensive, it takes a ton of time, and for most questions we have about the world, it's just completely and utterly impossible.
And that brings us to the final, most critical takeaway of the day. Since a census is usually off the table, the undisputed gold standard for proving causation is a well-designed experiment. By actively interfering, by doing things like randomly putting people into a treatment group or a control group, you can isolate the one thing you're testing and wash out all those sneaky lurking variables. It is the only way to truly prove that A causes B.
So, what does this all mean for you? It means you now have a new lens to look at the world. You've got the statistical secret decoder ring now. So the next time you see a headline that says, "Study shows a link between X and Y," you can ask yourself the million-dollar question. Did they just watch something happen, or did they actually do an experiment? Was it just a correlation, or did they really prove causation? You'll be amazed how often you find it's just another story about ice cream and sharks.